Adoption Drive. I'm your host, Hari Sripathy. We're here today to talk about the very frontier of mobility, as we do always. But that frontier of mobility is blocked today by a massive financial and technical bottleneck. Training an autonomous vehicle, or really any autonomous system, on the infinite edge cases of the road is prohibitively expensive and technically complex. In fact, new market launches can often take more than a year, sometimes multiple years. My guest today is trying to compress that entire years into 24 hours. I want to welcome Balint Pasztor from Diffuse Drive. Diffuse Drive is looking to bypass the physical data bottleneck and create troves of photorealistic video, replacing the grueling need for manual sensor processing. Could this just be the key to scale autonomy? Balint, welcome to the show. And I want to start off with asking you to obviously, look, we work on autonomous systems, both you and I, including vehicles. And it's the biggest challenge in sort of an autonomous system to identify and train for the literally infinite number of edge cases. You cannot possibly train for every possible scenario in every single city or every single environment. And it often ends up limiting what is an operational domain, right? Where a system can operate a robot, where a vehicle can operate in a street. And this is one of the most complex scientific issues of this entire industry. But tell me how you're breaking that complexity. How are you simplifying the world for us?
First of all, Harry, thank you so much for inviting me. I'm pleased to be here. I'm glad that you started with the clarification that it's not just cars, it's all the autonomous systems. Of course, we are concentrating on a little bit of everything, regardless they are manned or unmanned. But what connects them is autonomous systems. And coming from autonomous driving, both of us, I work for Bosch Level 4. And we had that problem seeing at all the edge cases, seeing at all the complexity that you cannot train for everything because you are limited by physics. You are limited by a budget. And even if the world is infinite, the budgets are not. So what you have to do is, of course, have the best alternative to that is collect data from the real world for AI or, well, what we mostly call this is machine learning. Way before that is to collect all the data that you can, right? But unfortunately, you cannot test for everything, or first of all, you cannot train for everything. And up until now, I would say that, well, all the edge cases, all the complexities you couldn't get. So the way that we were looking at it is that software is built iteratively. So why cannot data be built iteratively? Similarly, you as a child or anyone as a child, you didn't know everything when you were born. You iteratively learned about everything. So that's what we are trying to give to our partners, customers' hand, is to be able to build up all those data assets, or in other words, train the AI as you are gathering and uncovering more and more complexities, more and more edge cases, cover more and more in the operational design domain. And then practically same way how software is being built, or in this case, I don't like to use the word AI this many times, but at the same time, how AI is being built, every iteration builds on top of the previous one so that data can be also built the same way. When you are uncovering a bottleneck, you can just directly deploy into that. Unfortunately, the real world blocks you on that. The real world is scarce in complexities, in a sense that like you are only uncovering the edge cases every once in a while. I live in San Francisco. You see all the wonderful companies, Waymo, Zoox, just roaming around. Most of the times, they are seeing the same things, the same red light, the same cars roaming next to them. So similarly to that, they even in aerial autonomy, or just in a closed environment, in a factory line, you are seeing the same things. The edge cases are not uncovered. Please.
And it's a great point you make, but just to color, to provide some color on how much you're solving what the business case for the use of diffuse drive is. make a guesstimate a little bit of how much does it currently cost to launch, let's say, an autonomous vehicle or an autonomous system in a specific operation? What goes into that, and how much do you end up saving by using diffuse drive?
So I mean, you can look at it in many ways. One is, of course, we are saving engineering time. Whenever you are developing AI, a significant portion of your time is dedicated to data, and then that also, of course, entails filtering through the existing data, finding what's missing compared to an ideal case, and of course, get it from the real world, get it labeled, stuff like that. It will endure precious engineering time. And this is what we are practically eliminating, giving a digital data scientist or a digital engineer to our customers, to the hands of our partners. And then, yeah, practically eliminating that part. The other part is, of course, you have to pay physically deployed systems or people that are collecting data. That's another factor. So these are the two ways that we are sparing time and of course money. Some of our customers were telling us we practically give like a time machine to them. They can deploy faster because they have the underlying data collected.
That's a great point. But let me ask you a sort of product question, if you may. How do we know that synthetically generated photorealistic data is more comprehensive than just, let's say, observing the world? How do you, in other words, and how do you get to the asymptotic curve of edge cases? And I want to maybe summarize what you actually just said, which was yes, when you're driving in a real world, the chances that you observe an edge case is actually fairly minimal. But you're creating data that, represents, it's actually more. There are more edge cases in that data in order to train the system across it. But how do you actually solve for a comprehensive list of edge cases?
Now, that's a really good point that you're making. In itself, like a single data point is not any more comprehensive than another one. You are seeing multiple different things on a given imagery, let it be in electro-optical or in infrared domains later down on the line, like SAR, ISAR. These are like synthetic aperture radars or inverted synthetic aperture radars. The way that you should look at it is that the individual data points will culminate into a data set. And we are thinking about the data set level, how the complexity, how the diversity, how the edge case representation is there. And that's where it differs from the real world collects, how our customers are calling it. So the difference between that is that we are introducing diversity, not on the individual levels, but the individual levels culmination will give you the highest diversity. So here it's more like coverage by design is what we are giving into the hands of the developers. So of course, the other part is that we are actively learning from all of the deployments. Actively, the system on the foundation level is getting better so that when it becomes, when it gets to the deployment level, then it already is better from the get-go. And of course, those are silos. So these are not shared in between. And then the other part is, of course, like we can systematically just prompt the system to cover all these edge cases as opposed to from the real world. You can like simulate or stimulate an environment. There was a famous example. We were working on a little bit different radars, and we had to just practically just throw away some metal pieces. The radars are going bananas if there are metals on the road. And we are talking about cars here. When I was working at Bosch. And of course, you can stimulate it. You had like a couple, I don't know, like we had like a couple hammers throw down on the ground, but those are just stimulating the environment, catalyzing it. Unfortunately, in the real world, you cannot have these like God's hand or
Right.
placing
Hand of God.
the environment, hand of God, right?
Maryland.
So in this case, the uncertainty is higher. You're not gonna get those required and desired scenes. That's what you can do with synthetic data, right?
So really to summarize, you can tell the diffuse drive model, hey, have a basketball land on my windshield and simulate how my car will respond to that situation, even though that may never be very, very, very difficult to create in the real world.
Well, first of all, yeah, so we are talking about multiple different layers. We can talk about the perception layer, we can talk about the planning layer, or comprehensively the behavior layer. These are like covered by different models. Um, Lately, the word models are trying to simulate everything end to end. Uh, Altogether, that's practically how the domains are being covered. We can distinguish in many different layers, and I think that's gonna be the name of the game. There are dimensions in this, both on the development side for our customers, for our partners, and of course on the data side as well. It can be very well just deep level or very well higher level data, metadata for that.
Let me move you to sort of your go-to-market, and you're applicable across several different industries, industrial automation, robotics, of course, vehicles, both aerial and robo taxis, for example. But let me ask you a little bit about, your what's your beachhead? How ready are you for each of those various use cases?
I think the most important part is that we are where we are leading the most is aerospace defense, and more specifically because the scale is not widely ever available as much as for cars. So for them, so especially for autonomous vehicles, what is really important is the edge cases, the very edge of the technology, very edge of the data that they haven't collected, as opposed to everything else and practically anything else besides autonomous driving is one of those cases where you didn't even have what the scales of Tesla did, for instance. Tesla has this good couple million cars roaming around the streets. Waymo has all these collection cars collecting data from the world, stuff like that. So they are already at the point where for them, it's the very edge that they need, as opposed to what we are seeing is that there is no wide scale for most of the applications besides that. There is an extreme data scarcity, especially for aerospace defense, and it's just a high cost of the field action, the field collection, and of course the inaction is the other one. And the third one is, of course, there are a lot of safety concerns. So of course you need to go into the combination of all these, and
Right. So
that gives that, and also there is a pull.
right, your beachhead has high cost of inaction, of course, but large enough in scale and significant data scarcity where the problem is the most acute. And of course, you're following the robotaxi market, but it doesn't yet have that level of scale. But
And
tell us a bit
there is
sorry,
one more thing that I would like to add to that is that in aerospace defense is mostly simpler environments as opposed to what robotaxis and also the interaction with humans, the uncertainty or the complexity of an urban scenario, even like suburb or like outside of the city, it's still like super complex. The iteration cycles are fast still, but at the same time in aerospace defense, those are also given and the return on investment is higher for most of our partners, which is a super important part. At the same time, of course, we are following the robotaxi or rather like the autonomous vehicle space as well. We have worked with tier one suppliers on that.
let me pick up on one thing you mentioned, which is of course, Diffuse Drive actually well incorporates into the data models of the autonomous system itself.
Mhm.
Why not just build a data model yourself? And what is the difference, again, for a layman audience? Can you explain?
So the difference is in a sense, how AI is built up. You need to have the systems in place, and the systems comprise of practically three things. One is hardware. Right now, we are mostly talking about software. So the second biggest, of course, is software. And within that, you have the AI models, the algorithms, and you have the data layer. And practically the way that we are looking at it is since these are two separate layers, of course, not directly correlated. On the foundational layer or perception or planning layer, or at the combination of it on the behavior layer, you're working on the deployment, you're working on the algorithms, as opposed to on the data engine, data curation part, that feeds into that. So that's the fuel to it. And the way that we are building it is, of course, like we are building a neutrality to it. So it's not overfitting to the very specific use case. There is a faster adoption and, of course, a faster iteration from one data layer to another one. And of course, we are integrating into all to the domains. So that means that there is an active cross-domain learning. Um, at the same time, or at the foundational level, at the same time, of course, I think I mentioned this just a couple of minutes ago, there is customized deployment, there are silos. So when it comes to their own deployment to all of our partners, they are getting the best of the best from the foundational layer and being fine-tuned for their systems, which means, of course, it looks like, feels like, breathes like their own system. So that's the most important part. So what we are building here is the data infrastructure layer.
Absolutely.
How is being built for AI.
Let me sort of sharpen the pencil on that a little bit, right? To what extent is human intervention needed to, let's say, augment your either data capture or the data model itself? And if yes, how? And specifically in terms of actually reducing certain bottlenecks, there's obviously this concept of data offloads, which are data is periodically uploaded back to the cloud, and it's particularly edge cases, and that requires a significant amount of both storage as well as computing power on the premise for most robotic and autonomous systems. Now, are you actually, is a successful rollout of Diffuse Drive actually reducing that bottleneck? And to what extent is sort of human intervention or human augmentation necessary?
Practically what you're asking from me is that is it like no real world testing anymore? And yes and no at the
Yes, fair enough. That's a great question. Yeah.
yes and no at the same time. So in a sense that, of course, you have a set of resources, you want to concentrate those resources into where they are the most impactful. And what we are right now eliminating. So right now, what's happening is that we are taking away all the things that are unnecessarily ineffective. So getting the training data from the real world, and you can concentrate your resources, the physical deployment, the human intervention, the human collects, or the human verification where it is needed when you are verifying it, very specific targets. So in a way, we are meaningfully reducing, and you can targetedly use the resources in the real world. And then, of course, when you're asking no real world testing, I would say in the long run, that's where we want to get. That's where we want to get where AI is teaching AI how to work. Of course, we are talking about a huge word model or a huge data engine that is helping AI to get deployed in the real world. And then at the end of the day, your test will already be the real world deployment.
Absolutely. So let me ask you a question, sort of as to end the show, a broader question. So, are you really the solution democratizing autonomous systems? In other words, if Diffuse Drive is immensely successful, can a popular mechanic aficionado now start launching their own self-driving car? Obviously with regulations, but can I build my own self-driving car?
I think you had a really good point baked into the question, which is
Yes,
yes, it
get the
can.
licenses. You still need to get your maybe the car's license, not a driver's license, but yes.
Exactly. So if it's cars, if it's a robot, if it's a technical person that is bringing into that, can it be faster? Yes, it can be faster. Can it be more lean? It can be more lean. So practically what we are replacing here is the mundane task of collect data collect. That means they can deploy faster. So this is what we are giving, the faster iteration cycles. Um, if they are a legitimate builder and they can go through the legal hurdles, of course, autonomy has multiple bottlenecks. One of them is, of course, the engineering part. The other part is the regulatory. But besides the regulatory part, I think there is a good chance that a single person can deploy an autonomous car or an autonomous drone, or let it be just an autonomous household robot eventually, of course. I think where is really important is that since cheap data, or rather specific data that is comparatively cheaper to acquire, will essentially solve the iteration problem. You can deploy it to a very specific part, and then you can widely distribute it. That also means that as a humankind, we are benefiting from it. So there is a really interesting point on that. Is it gonna be cheap? And then we are getting to universal basic income, stuff like that. Is it gonna be everyone is gonna be out of their job? Stuff like that, questions. But I think a really important point is that it's gonna be a faster iteration cycle. we're gonna have a different problem to solve, I think. And that's gonna be it's not reckless, it's more like a tooling for raising the bar, or rather lowering the bar for the person.
Absolutely. Well, Balint Pasztor, he mentioned worlds are infinite. Well, budgets are not. Diffuse Drive is truly building the learning system for autonomous systems. In a world where education is the most expensive, Diffuse Drive is building that classroom, hoping to make testing and real world testing essentially not necessary in the long run. Hoping that one day a popular mechanics aficionado, you, listener, can build and launch your own self driving car, truly democratizing potentially transport, aerial transport, or at least a vacuum cleaner in your house. Uh, Balint, thank you so much for coming on the show, and I hope you all enjoyed this as much as I have. Thank you so much.